Welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. So question number 1, a hot air assumed as an ideal gas with Cp 1000 joule per kilogram Kelvin, gamma 1.4 enters a gas turbine. So gas turbine, so this is the gas turbine. So this will be your entry state 1 and enters a pressure of 10 bar and temperature 1000 Kelvin. So it's an ideal gas. So the gas flowing through is an ideal gas with the Cp and gamma value given. Then the exit. So turbine produces work output and the processes is reversible and adiabatic. So the process is reversible and adiabatic. That means isentropic. Then it expands in a nozzle. So at state 2, the ideal gas leaves the turbine at a pressure 5 bar and then it expands in a nozzle. So maybe we take, this is a nozzle, comes out. This is nozzle, the turbine. Thus we take it state 3 with a pressure P3, 1 bar. So the turbine, the process 1 to 2 is reversible adiabatic. That is isentropic. Process 2 to 3 is also reversible adiabatic. That is PV power gamma equal to constant. So this is valid for both. So what is asked? So what is the final velocity? V3. So this is what is asked. The final velocity at the exit of the nozzle. And it is given that inlet velocity of the air to the nozzle is negligible. That means V2 is approximately taken as 0. So we apply the steady flow energy equation across nozzle. For nozzle. So enthalpy, maybe here you have enthalpy H2. Potential energy and potential energy will be neglected. Okay, because nothing is said about potential energy, so we can neglect the potential energy. So we have enthalpy H2 and kinetic energy, maybe we will write down, then we cut those V2 squared by 2 plus G Z2. So reversible adiabatic. That means no heat transfer, no work transfer in the nozzle. No heat transfer, no work transfer in the nozzle. Okay, so this will be equal to, maybe the basic equation is energy in equal to energy out. So energy in Energy out. So potential energy neglected. So potential energy neglected. Kinetic energy at the inlet of the nozzle will be neglected. And we know that ideal gas CpT2, CpT3. So now we need T2 and T3. Cp is given. So for that, we exploit the reversible adiabatic process. So for process 1 to 2, T2 by T1 is equal to P2 by P1, the whole power gamma minus 1 by gamma will give you T2. T2 is equal to T1. T1 is 1000 Kelvin into P2. P2 is 5 bar. P2 is 5 bar because it is a ratio of pressure. So you can substitute in bar itself. Gamma minus 1, 1.4 minus 1 by 1.4. So we see what is the value of this. $820.33 is your T2. So we got T2. So now we go for T3. So from this process, T3 by T2 is equal to P3 by P2, whole power gamma minus 1 by gamma. So this gives you T3 is equal to T2 is 820.33 into your P3. P3 is 1 bar, P2 is 5 bar, whole power 1.4 minus 1 by 1.4. So now we will get to T3. Five 117.94 Kelvin. So you got T3, T2, and now you can substitute. Since your velocity you want in meter per second, velocity we want in meter per second, Cp must be substituted in joule per kilogram Kelvin. Cp cannot be substituted in kilojoule kilogram per Kelvin, okay, because V3 we will get in meter per second. So Cp 1000 Cp value into T2 820.33 thousand 5.94 plus. So now we get V3 in meter per second. 770.68 meter per second. So rounded up to one decimal place. So the answer will be 777.7 meter per second. So that is answer for okay, so now we move to the next question. So you are given a process 1 to 2, 2 to 3 in a TS diagram. So the heat transfer during the process 1 to 3. So we know that area under TS diagram is equal to heat transfer during the process. So that means this area, the entire area, this entire area is what is the heat transfer. This entire area will be the heat transfer in the process 1 to 3. So we need this area. We can take two areas. So this area has a trapezoid. Maybe this area A1, it is a trapezoid. And the other area is a rectangular area. So this area A2 equal to rectangle. So we want the answer in kilojoule per kilogram. So the entropy is kilojoule per kilogram, temperature in Kelvin. Entropy is in kilojoule per kilogram Kelvin. Entropy in temperature in Kelvin. The area will give you kilojoule per kilogram itself. So now the area A1 is equal to trapezoid, right? So we take this height as 300 Kelvin. This height 450 Kelvin. This distance 0.75 minus 0.25 equal to 0.5 kilojoule kilogram Kelvin. So now area A1 will be half into trapezoid area 300 plus 450 into the height 0.5. So this (187.5 kilojoule per kilogram). Area A2. A2 is the rectangular area. So you take this. This will be 0.75. 0.15 kilojoule per kilogram. So area A2 is 450. It is a rectangular area. 450 into 0.15. 67.5. So the heat transfer in the process 1 to 3 is equal to A1 plus A2. 255 kilojoule per kilo. So your answer is 255 kilojoule per kilogram. So now we move to question number 3. Next question. So if X and Y are two independent intensive property of thermodynamic system, then which relation among the following fails to identify Z as a thermodynamic property? So if Z is thermodynamics property, then the equation must be exact. Z is, if Z is thermodynamic property, then dz must be exact. So we know that dz equal to m dx plus n dy exact if dou m by dou y equal to dou n by dou x. This condition satisfied, then so maybe for A, if you look at m is equal to x, sorry, m equal to y. So whatever is along with dx will be m, dy will be x. So dou m by dou y equal to 1 equal to 1. So that means this is exact. A is exact. So this exact. So that means the Z is the property. Z is a thermodynamics property. Now come to second B. So here m equal to minus y, n is equal to x. So dou m by dou y. So here dou m by dou y equal to dou n by dou x. So here not equal to dou n by. So in this case, inexact. Z is not a property, thermodynamics property. So that means, so which relation among the following fails to identify Z as another thermodynamic property? That means B is the answer. Maybe we'll check the other two also. So we will take it C. M equal to 1, N equal to 2. Dou M by dou Y 0, dou X 0. So in this case also, this is exact. So Z is a thermodynamic property. M is equal to 1 by minus y by x squared. N is equal to 1 by x. So in this case also, so exact. So this also exact. So Z is the thermodynamic property. Only B is the equation inexact, and Z is failed to be a thermodynamic property. B is the answer for that. So now we will go for next question. So in a steady flow process, superheated steam at 70 bar and 450 degrees is throttled to 30 bar in an insulated valve. So you have a valve. So you are throttling. So this will be state 1, state 2. It is the throttling process. So in a throttling, so the pressure at this point, 70 bar, temperature 450 degrees centigrade. So corresponding and changes in kinetic energy and potential energy are assumed to be 0, and mass flow rate m dot, it's a steady flow device. So whatever mass is going through section 1 will go through section 2, and mass flow rate is 2 kg per second. Changes in the kinetic and potential energy neglected, entropy generation during the throttling process. So here enthalpy will be H2, here enthalpy will be H1, entropy S1, here S2. So we know from the throttling process, your H1 will be equal to H2. And since there is, the process is irreversible, the throttling process is irreversible, entropy generation is nothing but the change in entropy of the process. So the change in entropy of the process 1 to 2 in a throttling process is entropy generation. And nothing is said that the heat will be going out. So there is no heat loss. So there is no heat loss. Maybe it is completely insulated. So heat transfer is 0. Heat transfer is 0 in a process 1 to 2. Heat transfer will be 0 because it is completely insulated. That means the entropy change happens only because of entropy generation due to irreversibility. Okay, so entropy can come into the system two ways. One is entropy transfer, another is entropy generation. Since there is no heat transfer, no entropy transfer. That means only entropy generation, which is due to the irreversibility of the process, because throttling is irreversible process. So we need to find out this. So now you are given the property at 70 bar and 450. So 70 bar and 450. So you are given this. So that means your H1 and S1 are given. So H1 and S1 are given. Now we need S2. For that, another data is given, the at 30 bar. So data superheated at 30 bar. So 30 bar is this. So P2 is 30 bar. But at two temperatures, your enthalpy and entropy is given. We need to find out what is the temperature T2. So for that, we know that H1 is equal to H2 is 3288.3 kilojoule per kilogram. So now, so you can get it by interpolation. So what you do, you take this temperature here by a linear interpolator, H. So H1 is so you are given at 400 degree and 450. Maybe here I take it 450 degrees centigrade. Your value of H somewhere here, let's say. So 3, 344.9, and at the value of 400 degrees centigrade. So this is make a dot somewhere here. This will be 3231.7. Now this linear line, from that we want 3288. Maybe somewhere here, let's say this is the value 3288.3. Corresponding to that, what is the temperature? So this is T2. Temperature at the exit, T2. So this is what we want. Once we know T2, then from there we can find entropy. So using a linear interpolation, so what we do, so for T2 minus 400 divided by, so corresponding 32288.3 minus 3231.7 is equal to 450 minus 400 divided by 3344.9 minus 32.7. So we get the T2 in degree centigrade. Because here the temperature difference, so in degree centigrade, it will be the same. So we are getting the T2 by linear interpolation. Four 425. So you get 425 degrees. So T2 is 425 degrees. So now we get the entropy by using the linear interpolation. So we will so entropy versus the temperature. So there will be 450 degree, 425 degree, because in 425 degree only we want the then 400. So corresponding to that 400, you have a entropy value. $450 you have entropy value. So this the linear interpolation. This is what is your S2. This is what we want. Now for 400, if you go back, 400, 6 point, so this is the value of for 400, 6.9235. 6.9235 at 400. 400, 6.9235. Now at 450, 450 this. 7.0856. 7.0856. So now we need the S2, which is corresponding to 425 degrees centigrade. So use the interpolation. S2 minus 6.9235 by 425. 425 minus 400 equal to 56. Minus 450 minus 400. So now you get the value of S2. 7.00455 kilojoule per kilogram Kelvin. So this is your S2. Now you go back and find out. So our S2 will be 7.00455 kilojoule per kilogram Kelvin. So entropy generation is S2 minus S1. 7.00455 minus S1. S1 is at 450 degrees centigrade. 6 point. So S1 is here. 6.6353. S1 we write 6.6353. Point 36925. So the unit will be kilojoule per kilogram Kelvin. So what we want is in kilojoule per second Kelvin. So that means, so you have to multiply by your mass flow rate. So entropy generation is equal to m dot S2 minus S1. So m dot will be in kilogram per second. S2 minus S1 will be kilojoule per kilogram Kelvin. So this together you will get kilojoule second Kelvin. So you multiply by m dot. M dot is 2. 0.7385 kilojoule per second Kelvin. So it is asked rounded off to 3 decimal places. So that means your answer is 0.739. So now we move to question number 5. So the rate of heat received by a heat engine from a source. So you have a source which is 900 Kelvin. Maybe this we will be taking T1. So the rate of heat received by the heat engine. So heat engine rate of heat received is 600 kilojoule per second is 600 kilowatt. The engine rejects heat to the sink. (300 Kelvin). Sorry, it is Q2, it is rejecting to 300 Kelvin, which is T2. Produces work output of 200 kilowatt. What is irreversibility? I is the irreversibility. Irreversibility I is T0 into entropy of the universe or entropy generation. So T0 is the ambient. So here this 300 Kelvin, T2 is your T0 because the heat is rejected to 300 Kelvin is considered as ambient. Ambient will be around your 300 Kelvin is ambient temperature. So universe, so you can take this entire system as the universe. Change in entropy of the universe is equal to, so this is system 1, system 2, system 3. Entropy change of system 1 plus entropy change of system 2 plus entropy change of system 3. System 3 being a cycle, the entropy change will be 0. Because entropy change of a cycle will be 0. The third system is a heat engine, which is a cycle. Then entropy change of first system. First system is a thermal reservoir of 900 Kelvin, which gives out the heat. So minus. It loses entropy, Q1 by T1. Thermal reservoir, the entropy change will be Q by T. For any thermal reservoir whose temperature is constant, the entropy change will be Q by T. And since the thermal reservoir 900 Kelvin is losing the heat, so it loses entropy. So entropy change will be minus Q1 by T1. And the reservoir 2, which is atmosphere, thermal reservoir 300 Kelvin, which is taking the heat Q2. So entropy change will be positive, Q2 by T2. So Q2 minus Q1 will be 600 by 900 kilojoule per Kelvin. So you get kilojoule per Kelvin plus Q2. Q2 will be Q1 minus work output, because we know that the work output is equal to Q1 minus Q2. From there you get Q2. 600 minus 200, it is 400. 400 kilowatt. This is the entropy change of the universe. Point 66 kilowatt per Kelvin. So now the irreversibility. T0 is 300. Entropy change is 0.66. So this is in Kelvin, kilowatt per Kelvin. So irreversibility you will get 198. So this will be the answer. The irreversibility in kilowatt. So thank you for watching this video. So if you are happy with this video, please subscribe the channel and share this video to your friends who are preparing for GATE mechanical engineering subject. Those who want to join for GATE 2026 video course, please contact in the mobile number given here. And you can also go and see in the website given here. Thank you.